Page 5, another LOL or heat diagram. Tray of water is placed in the freezer and turns into ice cubes. Got some temperatures there, but the temperatures aren't really crucial to be graphed. We just need to think about how much heat there really is. What are we focusing on? Water. That is our system. It's a tray of water at 20. It's not real warm, but I'm going to give it 2 bars. If you want to give it 3, you could. The key here is it's not only going to turn into ice, but it's going to get to be really cold ice. Some of you might even go to a half of a bar. I'm going to just go with 1 bar. It isn't, I don't need to have a half bar, so I'm going to go with 1 bar. It's going to be really cold when we're done. It's going to lose a lot of heat. What about the phase? It started off as a liquid. Liquids have 2 bars, but when you turn it into a solid, it'll only have 1 bar. So I have 4 bars over here, changing into 2 bars over here. I just have to show over here that the water, let's see, did it get warmer or colder? It got colder, so it lost. How much? 1, 2 bars. I'm going to make sure that I show it going out. Next one. This is the type where we have to calculate how much energy. Now the numbers are important. Before we do anything, sketch the temp time graph. Be sure to include beginning and ending temps as well as the temperature during any phase change. Some of you could do the math without doing it, but yet the directions say we have to sketch the temp time graph. So we make sure that we put that into there. I ask myself, what's the coldest it needs to be? -25. Just throw that somewhere down there. What's the hottest it needs to be? 155. But you have to think of it like this. If it's ice, it's going to first warm up until it only gets to a certain number, and that certain number is 0. So nobody told me to put 0, but I'm going to have to. There'll be a plateau as it melts. Then it's going to warm up again, but only until it gets to 100, and then it's going to evaporate, and while it's doing that, there will be a plateau, and then it's going to go up to 155. This is telling me that this is a 1, 2, 3, 4, 5-step process. I have to figure out how much it heat it takes to do each of those processes, and then add them all together to get one final number. I've got some information. Got some information over here. I'll pull this down for now. I know it's going to be 5 steps as it slide this over. Yeah, don't want that to look like it was part of that. I must have slid this. Let me go back. Okay, it's kind of there. Slide this down. So it's 5 steps. The first step is it warming up. The first step, so there's going to be 5 steps. It's all based on 35 grams. So I'm going to write 35 grams, 35 grams, 35 grams, 35 grams. I'm going to write it 5 times because I have 5 different things, but it's all based on 35 grams. I can write myself some notes about how to proceed. Number 1, since there's a slope, it's going to be a Q equals MC delta T, or simply an MC delta T. 2 is a flat spot. What's happening at 0 degrees? At 0, it's melting. That would be heat of fusion. Fusion has to do with melting or freezing, so that's going to be fusion. Then at 3, the third step, there's also a phase change, or nope, there's not a phase change, there's also a temp change, another MC delta T. The 4th step is a plateau. It's at 100 degrees. That's vaporization. We'd call it boiling, evaporating, but it's heat of vaporization. Finally, the 5th step also has a temp change. It's an MC delta T. I don't have to write those notes. I'm just doing that to kind of guide me. So the first one is a Q equals MC delta T. I already got the mass on every single one of these. So what's the specific heat? Well, number 1, we have ice. Specific heat of ice is 0.5 joules per gram degree Celsius. What's the change of temperature? Well, it's changing from -25 to 0, so it's a change of 25. Don't put the negative sign there, just ignore that. The next one, number 2, is a flat spot. We said that was fusion. So I go find my heat of fusion. It's down here. And you just simply multiply by 334 joules per gram. The next one is another slope, another m times c times delta t. This is in between 0 and 100, and when you have water between 0 and 100, it is now liquid. The specific heat of liquid water is 1 joule per gram degree Celsius. Okay, spotted a mistake I was making, and I think I went back and fixed it. Hoping you can see that down here, I now changed. I had specific heats for calories. We've done our calculations in joules. So instead of starting the video over, I changed those to 2.1, 4.18, and 2.1. That means that I'm also going to have to go back to this one up here and change this 0.5 to 2.1. 2.1. And then I have to change this 1 to 4.18. I now can pick up where I was at. I was in the middle of an MC delta T for the third portion, and the third portion was 35 grams of liquid water, 4.18. The change of temp to get from 0 to 100 is a change of 100 degrees Celsius. Heat of vaporization in joules takes a lot more heat to make something. This is the fourth one. Takes a lot more heat to make something evaporate, to jump out of the pan, to jump out of the container. 2260 joules per gram. Finally, the last section, number 5, is steam. Steam has a specific heat of 2.1 joules per gram degree Celsius. It will change in temp from 100 to 155, which is a change of 55 degrees Celsius. I pressed pause, did the calculations. Somebody better check them to see if I did them right. And if I add all of these things together, and I'm going to put this down here, I got on my calculator 111,299.5 joules. Really not very confident about that one. If somebody finds that I made a mistake on that, that wouldn't surprise me. Let me know.